Hello and welcome. My name is Mohammed Tariq, and I'll be taking you through your DeepPumas onboarding material. And this is the first unit of that. And the first question that we try to answer in this unit is why DeepPumas? What's so special about DeepPumas as a tool? And basically, there are a couple of things that are special, but really one of the most special things is that it makes it really easy to combine components of machine learning modeling and components of scientific modeling. So let's say you have your scientific model that you spent many months working on, perhaps many graduate students over the years have polished and improved to fit different kinds of data sets. That model is quite rich and encodes a lot of scientific understanding, a lot of hierarchy in the data, and that makes it also quite data efficient. So typically we don't need that many data points to actually fit a model that encodes a lot of mechanism that's not, let's say, completely flexible or completely black box. And so that also usually means it's a transparent model, it's an interpretable model, because again, we spent time developing it, we know what each parameter means, we made sure that the parameters are identifiable, and so we assign a certain meaning to each parameter, and that makes it much more easy to understand and to communicate what it means and what it does. This also makes it quite useful if I'm trying to do something like dose optimization or counterfactual simulation. People usually trust models that basically have the scientific mechanism or the underlying mechanism encoded in them if the scientists really agree on that mechanism. Now, this kind of modeling sort of tool is quite powerful and it's been used quite extensively in pharmacometrics and beyond, but there are some limitations to this, which is that it's mostly quite labor intensive. It takes a long time to actually figure out exactly which model to use if you have a very specific, perhaps complex data set that you've never seen before. And so often there's a lot of trial and error to try different absorption models, different clearance models, different, let's say, drug effect models. And so this can make it quite time consuming to develop these models, and it takes a lot of expert hours essentially to develop these models. Another sort of disadvantage is that it can miss on not unintuitive relationships by definition, because it's a model developed by a scientist who understands or tries to encode their understanding of the mechanism. If there is some relationship that's not yet understood, then we cannot really encode this in the model. And so these non-intuitive relationships that are difficult to reason about from first principles, perhaps because the data itself is very high dimensional or rich, like if you have image data, for example, that kind of, or those kinds of relationships and this kind of data will most likely not be fully utilized with scientific modeling, and we will need some other tool to try and extract information from that. And so these non-intuitive relationships that, again, haven't been understood yet, as well as the complex data and the ability to use complex data, all of that is sort of a weakness of scientific modeling. Now, on the other hand, we have machine learning modeling, which allows us to basically throw the data at the model. We have very flexible model structures, like a black box model that you throw data at it and it just tries to figure out what the relationship is between the input and the output. And so it's quite flexible. It allows you to do automatic model discovery. For example, if you pair it with something like symbolic regression, so you can use it as a starting point and then use the model that you get, which is a black box model, and some explainable machine learning techniques to figure out, for example, which of the inputs are affecting which of the outputs. And then you could use that to generate hypotheses. And so it allows you to do this automatic model generation and discovery and finding these non-intuitive relationships between your data, between your inputs and your outputs, and handling complex data. If you have an image data, no problem. We have certain architectures of neural networks and machine learning models that can understand or that can process at least these high dimensional images and then extract information from them to perhaps predict some quantity that you care about. And so machine learning models tend to be really good at predictive analysis or predictive modeling, and tends to be really good when you have a lot of data. Now that brings us to the limitations of machine learning models, which is that they often lack we lack the scientific understanding of what the model is doing. So any kind of attempt to explain what the model is doing is usually happening after the fact, after the model has been developed. And we try to sort of figure out exactly which inputs are affecting which outputs, but it wasn't really built into the model from the beginning. And often, because the models are so flexible and they can fit any kind of relationship, they require a lot of data to basically truly learn something meaningful, or the signal in the data rather than the noise. Because if you only give it like a very small data set and it's a very flexible model, then it's very easy for that model to essentially fit all of the noise in the data instead of the actual signal. And that makes it basically useless and if anything, harmful if you end up overfitting and not being able to generalize. And so pure machine learning tends to be much more data hungry than perhaps scientific modeling. Again, intuitively, if you have the linear regression model, for example, that describes if I know the relationship between an input X and an output Y is linear, I only need 2 points to actually fit the linear model. Right? Maybe a few more points if there is noise to tell the noise from the signal. But if you have a machine learning model, very complicated model, even if the true relationship is linear, it will take many, many more points to actually figure out that the relationship is linear, because by default it will try to fit every single point, essentially, and it has enough parameters to do that. And so in order to prevent it from overfitting, you need to take other kinds of measures, or you need to have a lot of data in that case. And so this tends to be a limitation of machine learning, is, again, if you want to do anything meaningful with it, you need to have a fair amount of data to do that. Now, often it's not as big as people imagine, so depending on the machine learning model, you may not need actually that much data, but still significantly more than perhaps scientific modeling, because we encode a lot more structure in scientific modeling, which makes it much more data efficient. So obviously machine learning models are also much harder to explain. There are techniques to try and explain what the inputs are doing in the machine learning model, or explain how a machine learning model reached certain predictions. If it made a certain prediction of a predicted value of output Y given input X, then there are techniques to try and actually reason about exactly how it reached that prediction. But in general, again, those techniques are sort of post hoc or after the fact, and they also don't give you a whole lot of insight. They often give you some information, but not the full understanding of what the model is actually doing under the hood. So with DeepPumas, the hope is that we're able to actually combine knowledge and data. Knowledge meaning your scientific modeling that you have from the literature, again, developed over many decades by many scientists and graduate students, and we don't want to throw all of this wealth of knowledge away, but at the same time, we also don't want to throw away some very rich data that we might have access to, like medical images or certain biomarker data that we measure, certain omics data, maybe wearable device data. There's a lot of rich data that we could potentially try to benefit from when developing our models for let's say, drugs and diseases and patients, and how they interact with each other. And we want to combine all of this data at the same time with all of the knowledge, all of the structure that we have developed, all the structural models and the mechanistic models that we developed over the years. And so really the ability to combine these two together in the context of, let's say, hierarchical modeling and nonlinear mixed effects modeling is what DeepPumas is all about. So really bringing the best of both worlds together, but also trying to avoid the worst of both. And we'll see how we can do that. And this really has applications across the board, in fact, all over healthcare and even beyond. But in perhaps in drug development, we can apply this methodology from lead generation to clinical research to market research, quality by design, and even individualized patient management. Really, in any application where you have some data, you have some models that have been developed, scientific models or mechanistic models that tend to describe the data reasonably well but are not perfect, and where we have a lot more rich data coming in that we could use, and non-intuitive relationships or things that like relationships that the scientist hasn't really discovered yet. And so in any kind of application where we have a scientific model and some additional data, rich data, where the scientific model is also not perfect, there is really an application for DeepPumas there. Of course, in this course, we will focus a lot more on perhaps pharmacometrics applications, but the application of DeepPumas can go beyond that. Now, let's get a brief understanding of something called nonlinear mixed effects modeling, and we'll see different ways to look at this class of models in the next presentations or in the next few videos. But basically, the idea of a nonlinear mixed effects model is that we're trying to model this hierarchical data, or this data across multiple patients. So let's imagine each one of those trajectories here is a specific subject or a specific patient. So these could be drug concentrations over time for one patient, and then we have different trajectories or different time series data for different patients. Now, the idea is that we know that this dynamics is governed by some differential equation system. So we usually assume that we have this sort of structure of the dynamics, and this structure has certain parameters like Ka, the absorption parameter, Cl, some clearance parameter, and Vi, some volume of distribution parameter. Now, those parameters are unique to each individual, and so they're not really the same parameter for every person. Every person has slightly different parameters, and so the way we define these parameters is as a function of essentially three things. One is something called the population level parameter. So this is a parameter that's shared between all of the subjects, and then some individualized parameter. So that's a parameter that's per subject, and then some covariates as well. So this here is some property or some measurable quantity about the patient, essentially. And so these individual parameters are essentially a function of some shared parameters between all subjects, some individual parameters, and then some covariates measured for each subject. And then those random effects, which is the individual parameters, eta here, we often call them random effects. They're often given some distribution like this, which is just a distribution centered around 0. And they represent essentially, or the covariance matrix of this random effect represents how much variability between the patients there are. Or there is. So the higher the omega is, essentially, the more variability in this eta value, and the more variability also in these parameters Ka and Cli and Vi. And so the amount of between subject variability that's not captured by the covariates, so if we ignore the covariates for now, this here is the same. Theta will be the same for all subjects. Eta will be a different value for each subject, and depending on how large the omega is, essentially that represents how different the different subjects Ka and Cl and Vi values are. And so that kind of information or variability is captured by this omega. The covariates, they represent again some variability or between subject variability, but it's captured by the model. So it's something that we have a relationship for it. So let's say we know that age affects absorption in a certain way, and weight affects the volume of distribution in a specific way. And so we can measure age and weight, and then we can explain some of the between subject variability through these covariates, but it doesn't really explain all of it, and therefore we try to have some additional parameters here that are individualized parameters or subject-specific parameters to capture the remaining between subject variability. As you can see here, this variability is a systematic variability, or it's a systematic difference between the subjects and not just some random noise. And so maybe in a more classical machine learning context, you would just fit a curve through all these points here and treat all of these points basically as noise, but that's not really the case here. And what's happening here is that we actually have fundamentally different absorption and clearance and volume parameters that actually govern the data generating process. So this whole thing can be called the data generating process, where we assume that the values of eta are sampled from this distribution, and then every subject gets a different eta and gets a different Ka, different Cl, different Vi, etc. And that represents this data set here. And so this kind of model structure, where we have population level parameters, where we have random effects, and where we have some covariates, and the population level parameters, for example, are all these parameters here that are except for eta, and where we have some model, not necessarily a dynamical system, but often it can be a dynamical system, in pharmacometrics at least, it usually is, and then we have some error model, so this is some observational noise on top. This kind of model structure is often called a nonlinear mixed effects model. And we will see a lot more examples and insights into how to understand what this model is actually doing, and how to incorporate machine learning into this. Now, a neural network is essentially nothing but an information processing mechanism. So we did mention that we're going to be combining machine learning and scientific modeling. One of the most prominent families of machine learning models is a neural network model. And again, it is nothing but an information processing mechanism. We'll see more details about this in the future. This is just an overview of sort of what a neural network is. And the nice thing about it is that it's a universal approximator. And so if you look at this nice video here, you'll see that regardless of what the function, the true function f of x is, the true function f of x here is, the neural network, given enough data, can actually morph and change and take the shape of that function f of x. And so it is a universal approximator in the sense that it can actually fit any kind of input-output relationship given enough data with a certain precision. And so if you have a lot of data provided to you, then you can actually, the neural network is able to fit any kind of input-output relationship, essentially. And therefore, that property makes it quite powerful and quite useful to use in certain contexts where we know that, for example, a certain variable y depends on a certain variable x, but we don't quite know what this relationship is. So let's say we know that x causes y, or x is associated with y in some way, but we don't know exactly what the functional form is, and therefore we can make use of a neural network to try and capture that functional form. Now, a neural network has this kind of structure, and again, we'll see more details in the future videos, but it has often a few inputs, some hidden layers. In this case, I just show one hidden layer with 4 hidden nodes, or neurons as they're called, and then 2 outputs in this function here. And so it's loosely based on the idea of a neuron in the brain, but really that's a very loose analogy, and it's just a mathematical function. It's like fundamentally, at the end, it just boils down to a function that has some parameters. So each of those edges, each of those arrows has some coefficient associated with it, and therefore we just try to fit those parameters of the function. So fundamentally, and mathematically, it's just a function that we can use anywhere where you would use a normal function. So if you ever used exponential or an Emacs function anywhere in your model before, you can also just use a neural network function, essentially. And so they're usable anywhere where you would use a function. And that, again, can be quite powerful. And so let's imagine that we don't actually know certain covariate models. Let's say that we have some part of the covariate model here. We know how age affects the absorption rate, but we may have some additional data like images or omics or something like that, and we don't quite know how they affect the individual parameters. And so we'd like to study the relationship between those rich data, this maybe, let's say, rich biomarker data, or this image data or omics data, and how it affects these different properties here, or maybe the molecular structure of the drug itself and how it affects these different properties here. And so there we could potentially use a neural network to try and figure out this relationship, essentially. So we still have our own model that we developed from before, but then we now have additional types of data that we could not really process before, we could not reason about before. But if we have a neural network that's able to extract information from this data, then we could just throw the neural network in there and then try to ask the neural network, or try to fit this neural network such that it maybe predicts or figures out how to predict the outcome better, given this information that we have newly available. And so again, we can use the existing model, but then also try to enrich it and enhance it with machine learning plus some rich data that we didn't know how to use before. Right. Now, similarly, we could also have a neural network here to describe some part of the dynamics. And so not just a covariate model that could be used or that could be learned using neural networks, but also your dynamical system could be partly learned using a neural network. And so if I know, for example, how the absorption works, but I don't quite know how the clearance works, then I could just put a neural network here to try and capture the relationship or the functional form, essentially, of the clearance rate of change. And that could help model different complicated drugs and like the behaviors of the clearance of different drugs. If it has a nonlinear clearance or time-dependent clearance or something like that, then all of this could potentially be captured directly by the neural network or learned by the neural network, instead of a scientist trying to guess different functional forms. Now, often a modeler will be trying different functional forms, trying different models, seeing which one fits the data better. But then at the end, if you really don't find anything that fits, you have to sort of improvise and come up with something that may be time dependent or may have a certain nonlinearity basically in the clearance or in the absorption part. And the idea here is we're saying, okay, if you know what the structure is, if you know what the mechanism is, great, you can use that knowledge. But if you don't, then you don't have to guess. You could just put a neural network in there and ask it to figure out what the best relationship is between, for example, the drug concentration and the clearance rate, or between the drug concentration and the absorption rate, and it will just figure out the best relationship that best fits your data. Right, so it will figure out the relationship that has the best fit of your data, instead of you trying to just guess different functional forms. So that's really another very powerful application that we will see a lot of for this, using neural networks and using machine learning together with scientific modeling. So here we didn't actually have to throw all this model away. We have quite some knowledge encoded here, in that we have linear absorption, we have conservation of mass, so the drug leaving depot is going into central. All of this knowledge is fundamental to data efficiency. If you want your model to be data efficient, if you don't want to require many data points or many observations per subject, you need to encode as much of this knowledge as possible in your model. And it may seem trivial, but it's actually not. It can help you learn and fit your model and understand or identify these parameters using much fewer data the more structure you encode. Right? And so we didn't throw away the rest of the model that we knew is roughly correct or matches our scientific understanding, but we still used the neural network in the parts that we felt the need to use it, where we felt that the model was misspecified, for example, or that we could use more rich data, for example, to inform that part of the model. Right? And so by precisely and selectively using neural networks in specific places in your model, you can actually sort of combine the benefits of both scientific modeling and machine learning at the same time. And that's what we broadly call deep NLME. Now, the neural network, as we said, is just a function, right? It can take any inputs and give us any outputs depending on how we want to employ it in the model. And so, for example, some of the inputs could be covariates, if we want to put it in the covariate model part to inform, let's say, absorption rate or clearance rate. Some of the inputs could be dynamical variables, if we want to use it in the dynamics, for example, to inform the rate of clearance or the clearance rate or the absorption rate. Some of the inputs could be random effects, even if we want to use the neural network and make it individualizable. So the neural network can capture a function that's actually different for different individuals, and it's parameterized by some random effects. So some of the inputs here could even be a random effect, right? And we'll see maybe more the interpretation of that in the future slides. But essentially anything could be input to a neural network, even time, the amount of drug, etc. And for every one of those types of inputs, you have different applications. And so you could, again, input the covariates and maybe some random effects, and you have a covariate model. You could input dynamical variables, and you can then use it to learn the dynamics. You can even use it here and use it to learn, for example, the relationship between the PK and the PD. So you can input the PK and then expect it to output the rate of change of the PD. Or the pharmacodynamics variable. And so you can use it in any place that you would use a normal function, essentially, in your model. And that's really the power of DeepPumas, is it makes it so easy to actually start plugging in those neural networks in different places to test your hypothesis quickly that, okay, does this input actually affect this output or not? Then you don't need to guess the functional form. Just put a neural network, test the hypothesis. If it finds something great, then you can dig into it and figure out what exactly it found. But if it didn't find anything, then you have basically you can reject that hypothesis that most likely this input does not actually affect this specific quantity that you care about. And so the ability to just employ these neural networks quickly to see if any biomarker, for example, is predictive of your clinical endpoint, any specific covariate is predictive of certain individual parameters, testing all these hypotheses, understanding is there a feedback mechanism, for example, that you missed in your dynamics. All of these things can be very quickly tested using neural networks and the deep NLME methodology. So to summarize, we basically would like to combine, or we've successfully combined, a bunch of different areas of statistics and machine learning. And so we have the mechanistic knowledge that we often encode using dynamical systems. And then that means in DeepPumas you can actually write your dynamical variables or your dynamics equations and ordinary differential equations to encode this kind of dynamics or mechanistic knowledge. We have the machine learning, where you can basically have neural networks take as input all sorts of data and different dynamical variables and longitudinal biomarkers and so on to again extract information from them and then use that in your model. And so we have the machine learning component, we have the dynamics component, and then we also have the nonlinear mixed effects modeling component, which is arguably one of the most important components and fundamental components here, that allows us to model this hierarchical data, this idea that we have some data per subject, and then we have some shared parameters between all the subjects. We have the dynamics is usually shared between all the subjects, and then we have some individual parameters and covariates and so on. So longitudinal data of multiple subjects in a population, and modeling that data over time is often done using nonlinear mixed effects modeling. Now, PKPD, or pharmacokinetics and pharmacodynamics, often combines dynamics with NLME quite frequently. So there's an area called mixed effects neural network, where you also have machine learning or neural networks with random effects as input, essentially, and then you have something called a mixed effects neural network. Now, if you have scientific machine learning or machine learning combined with some dynamical system that encodes mechanism, often this is called scientific machine learning or universal differential equations. And so deep NLME really sits in the intersection here, where we try to combine all these components together. So we have the nonlinear mixed effects modeling part, and then we have the machine learning part, and then we also allow dynamics to be combined with all that. And so DeepPumas really is at the center of all these three, and you can do just one of them. If you want to just do machine learning, you can. If you want to do an intersection of just two of these, you can. But if you want to do all three at the same time, there is really not that many, or there are not that many tools out there, or almost any tool out there that can actually enable you to do that with that much ease and just user friendliness. And so DeepPumas is really one of a kind of tool. And this concludes our first unit. Thank you for your attention, and looking forward to our next unit.